let's graph some piecewise functions. In a previous video, we talked about evaluating piecewise functions. Now let's talk about graphing them. So we've been given a piecewise function, h of x is equal to 2 if x is not 0, and negative 3 if x is 0. This is actually a very specific type of piecewise function. If you see something like if x is equal to a particular number, it's this, that's telling us to plot a point. It's just a point. So if x is equal to 0, if we think of a coordinate point, x comma y, if x is equal to 0, the y value is negative 3. So we have the point 0, negative 3. So that if we look at this graph, and we go to if x is 0, the y value is negative 3. We're good there. Everywhere else where x is not 0, it should be 2. This is going to be just a straight line, a horizontal line, at 2. But it doesn't exist. So here we go. We have a line, 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 line. It doesn't exist at 0. It doesn't exist at 0. Because we only use this portion of the function if x is not 0. And that would be the graph. That would just look like that. Normally it wouldn't be different colors. We would just make it into like black. And that would be what the function would look like. Let's do another one. Suppose the function is defined below. So we have to be careful here. Right? We have to be careful. The function is negative 1 if x is between negative 1 and 0. This includes 0 and it doesn't include negative 1. So the line negative 1 in general would look like this all the way across, right? That's the line negative 1. But we're told that it starts at x equals negative 1. So that's going to be right here. And just kind of adjust it. And there is no underline under this inequality. So we don't include the point at negative 1. This goes until x equals 0. It goes until x equals 0. There is an underline there, so we're doing a solid circle. So just really important to remember, these underlines here, these correspond with solid circles on the graph, whereas no underline, those exclusive inequalities, those ones are open circles. So there was an open circle at negative 1 for this piece because it didn't have the underline. There's a closed circle at x equals 0 because it did. All right. 0. If x is between 0 and 1, the value of the function is 0. So the line 0, y equals 0, is just this line right here. But this line right here only exists between 0 and 1. So let's bring it on over to x equals 0, which would be here. We are putting an open circle because there's no underline there. Let's do a nice open circle. And it only lasts up until 1. So I'm going to shorten it down till x equals 1. And there is an underline, so I am doing a closed circle. For this next portion, between 1 and 2, the value of the function is 1. What color haven't we used? We'll do blue. The value of the function is 1. So the line y equals 1 would look like this. But this portion, and maybe I should kind of highlight what I've done here. There we go. This portion only exists between 1 and 2. X equals 1, x equals 2, right? I'm looking down here at the x-axis. Then I'm determining whether I'm doing open or closed circles on each of its endpoints. So at 1, there's no underline. I'm going to do an open circle. At 2, there is an underline, so I'm going to do a closed circle. Finally, we have this last portion at y equals 2. Again, it would look like this, but we have it limited to just between 2 and 3. So between 2 and 3. Open circle at 2, no underline. Closed circle at 3. Open circle, closed circle. And that's what my graph would look like. Now, it wouldn't be color coded like this. It would all be in black. But that's what my graph would be. These functions right here are a little bit different than what we typically think of when we think of piecewise functions, which is going to be something more like this example that we're about to do. And then also, oh man, did I really put that many examples on there? All right, guys, we're really in for it now. I put too many examples on here, but we're going for it. Let's do it. All right. First things first, I'm going to take care of the easy portions of this piecewise function first. If x is less than -2, the y value is -1. So y value -1 would be this entire thing here, but it only exists for x less than -2, so that portion. There's an underline, so I'm doing a closed circle. That goes off forever. That portion, done. This one has the y value 3. The entire line would go this far, but it says that it only exists if x is greater than 2. So I am going to shorten this guy up. There is an underline on the 2, on the inequality there, so we are doing a closed circle. Excellent, excellent, excellent. Finally, this middle portion, x plus 1 is a line. Think y equals mx plus b. We need to plot 2 points on a line in order to make a line in general. You need 2 points on a line to graph a line. What we're going to do with lines and piecewise functions is we're going to plot a point at one of the endpoints and at the other. So we're going to plug in these values, even though they're excluded, right? Even though they're excluded, we're going to plug these values into this function so that we can get 2 points to plot on the graph that will be open circles. So this will be an open circle at x equals, that'll be x equals -2. It'll be an open circle because there's no underline. So -2 plus 1, because we're using the x plus 1, is -1. So we have an open circle at -2, -1. All right. Interestingly enough, there was already a point plotted there, so it doesn't matter. For x equals 2, using this function, we're doing an open circle. Plugging in 2 to this function, x plus 1. 2 plus 1, that's 3. This is the point 2, 3 that we have an open circle at. And goodness gracious, there's already a circle there. So we have 2 points on this hypothetical line. We can connect them together. And that's what my graph looks like. Let me change it to black so you can see it all as one. It just looks like this. It just looks like this. So for each of these pieces, you're especially for lines, you need 2 points to plot a line. So you need to plot a point at each of the ends that it's good for. All right. Suppose that the function g is defined for all real numbers as follows. Graph this function. This is similar to that first example, but different. As long as x isn't equal to 2, it's the line negative x. Negative x has a y-intercept of 0 and a slope of -1. So it's going to go like that, right? This would be the line y equals negative x. But it says at 2, the value should be 2. So we don't look to it. Let's see. We don't use this portion of the graph if x is equal to 2. So at that portion, I'm going to put an open circle to denote that there's nothing there. Nothing. Then at x equals 2, it says the y value should be 2. So I'm at x equals 2, and I'm going to plot, boom, a point right here. And that's my graph. This point that oh, that's right, because there you go. This point right there that I plotted at the intercept when I was plotting the line, you don't need to plot that point. Really, it's just a line, open circle, where we put this point up here. And that's it. That's it. It's done. All right. We have another function, but this question asks an additional thing here. It asks whether or not the function is continuous, which we won't know until we've graphed, but let's talk about what continuous is. Continuous means that you can run your pencil along the graph without lifting it up. If I look back at these previous graphs, this graph is not continuous. If I run my mouse along it, I would get to here, and in order to get down to this point, I would have to jump. I would have to lift my pencil up. So this graph right here is not continuous. This one right here, there's a lot of jumping. I can go to here, but I have to lift my pencil to get to here. Lift my pencil to get to here. Lift my pencil to get to here. This is not continuous. This guy is continuous. So I start here. I don't have to lift my pencil. I don't have to lift my pencil. I don't have to lift my pencil. I didn't run into any holes or gaps or anything. This is continuous. This one right here, much like the first graph, not continuous. There's a hole in it. If you see a hole in a graph, it is not continuous. All right. So there's that. Now, no. Let's graph. Let's graph the line 5x minus 4 if x is less than or equal to 1. I can graph this line. I can graph this line without that restriction quickly to just graph it, just because. Y-intercept is -4. The slope is 5, so I'm going up 5 over 1. I'm going to plot that point, and I think, let me plot a few more points. I'm going to have to delete these later. Up 5 over 1, up 5 over 1, down 5, left 1. Okay. So if I were plotting this entire line, it would look like this. But they say, hey, No, we don't need you to plot the entire line. This is only true if x is less than 1. And where is x equal to 1? Let's see. Less than 1 is everything here. So starting here at 1, we need to get rid of the rest of it. Okay, so that's what that portion looks like. There is a underline here at 1, which means that we do have a closed circle. Negative x plus 4 if x is greater than 1. So negative x plus 4, that line is going to look like, I'll just extend it infinitely. This would be the line negative x plus 4 if it went the entire way, but it says it's only true if x is greater than 1. So I am truncating it, boom, to right there, and then asking myself the question, should I put an open circle or a closed circle where the line starts? Because there's no underline, I am putting an open circle. I'm putting an open circle, and that's my graph. Now, if you wanted to do this potentially the more proper way, and I can delete all this. Oh, no, I cannot delete all that. It's going to get mad at me. The more proper way of doing this is to plot points at each of we call them like breaking points, where the function breaks up. So plotting the point 1 comma, what happens if you plug 1 into this function? 5 times 1 is 5, minus 4 is 1. So you would have the point 1, 1 with a closed circle because there is an underline. And then I would choose a number less than 1 to plug into this function to plot another point. So I would choose a number like, negative 8. Negative 8 is less than 1. So if I plug in negative 8, to this top part of this function, 5 times negative 8 is negative 40. Oh, that's going to be too far. Not doing negative 8. We're going to go ahead and do negative 4. Wait. Nope, we're not going to do negative 4. We're going to do negative 2. Nope, negative 1. Negative 1. We'll do negative 1. Negative 1 times 5 is negative 5. Negative 5 minus 4 is negative 9. So we're plotting the point negative 1, negative 9. I'm connecting these 2 points because they're aligned. Bam. So again, I chose to plug 1 in for this function because it's at a breaking point. I did a closed circle because there's an underline. To graph the rest of the line, I just chose any number less than 1. But if you choose too far back, it's off the graph. So I chose negative 1 because negative 1 is less than 1. It'll give me another point on the graph. All I have to do is plug it into the function. Then here at 1, we're going to have an open circle because 1 isn't really included in the domain of the second portion of this piecewise function. If you plug 1 in to this function, though, you'd get negative 1 plus 4, which is 3. 1, 3. Why are you doing that? There we go. 1, 3. So that is an open circle, right? And if you want a trick here, you can just plot, we have the slope, we can just say, okay, the slope is -1, down 1 over 1, down 1 over 1. Come on. Oh, my nib on my Apple Pencil got loose. Slope is -1. We can just give it a slope of -1 the entire way. Bam. Okay. One more. Last example. Let's do this. All right. Let's talk about those breaking points again. Let's talk more in detail about the breaking points. This graph breaks up at -4 and at 4. Each of these pieces, you need to have open or closed circles for any number that's included over here. So we need to have an open or closed circle for this portion at -4. For this portion, we're going to need to have an open or closed circle for both -4 and 4. And for this one, we need to have an open or closed circle at 4. First one is 8 if x is less than -4. So less than -4. We'll just draw our line at 8 all the way across to begin with. This is a line at 8. If we only want it to be true less than 4, -4, then it would go to here. No underline. So open circle. Next portion, -10 plus x squared. At -4, if you plug -4 in, you're going to get 10 plus -4 squared. That's going to give you, let's see, -10 plus 16, 6. So this is the point, -4, 6. There's an underline, so it's a closed circle. -4, 6, closed circle. We're going to have to look at 4 as well. At x equals 4, if we plug it into this portion, which I understand isn't really included, right? It's not really included because there's no underline. That's okay. We'll put an open circle. 4 plugged into this function, -10 plus 4 squared. That's going to be not 16. It's going to be 6. So this is the point 4 comma 6 with an open circle because there's no underline. We'll finish drawing the rest of that portion in a sec. Let's just get our dots done. Here, for x greater than or equal to 4, we use 2x minus 2. So for this guy, we'll do x equals 4, plug it in. That'll be 2 times 4 minus 2. 8 minus 2 is 6. So we have the point 4 comma 6. 4 from the x value, 6 from plugging 4 in. It's a closed circle because there is an underline. So this is closed. So there's a closed circle at 4, 6, which is interesting because there was an open circle there to begin with, but we can close it up with our peak. Lines are easy enough. This is for greater than 4, so it's going to be over on this portion of the graph. Really, like if I wanted to like kind of like highlight, like the green portion should be all the way over here. Anything over here should be just green. For blue, blue is between -4 and 4, right? So this portion should just have blue graph. Over here, this should just be pink graph. So the line is 2x minus 2, so it has a slope of 2. I can start right here, up 2 over 1 point, up 2 over 1 point, up 2 over 1 point. And it just goes on forever. Now let's talk about this guy, -10 plus x squared, because that's a parabola. That's a parabola, right? This could be rewritten as x squared minus 10, and we just talked about transformations. This is x squared shifted down 10 units, right? So normally x squared would have its vertex at 0, 0, but because it's been shifted down 10 units, its vertex is right here. Normally, so here's what would normally happen. Normally, x squared would have a point at -1, 0, -1, 1, 0, 0, and 1, 1. But all of these points get shifted down 10 units. Okay? And then we're just making a parabola shape because the rest of it's just a parabola. And it looks like that. And that's our graph. That's the whole thing. And it looks like this. Question, is it continuous? The answer is no. It almost is. This portion right here is continuous, but right here, I would have to lift my pencil up, back down to get to this piece here. So it's not continuous. And I don't know if I answered that for the last question, so let's go look. Oh, this guy here, not continuous. So we would come here, jump, then go down, so not continuous. So that's that. This is a thing that takes practice, all right? This takes a lot of practice. It takes time, so give yourself patience. You're gonna be fine. If you have questions, send me an email. Otherwise, I hope your day is fantastic. I'll see you in another video. Bye.